Okay, let me get right into it. So at last year's conference and in a recent transactions publication, we presented a non-contact laser ultrasound system that overcomes many of the limitations of current non-contact ultrasound, laser ultrasound systems. First of all, it's very compact. You can see that our source laser you can hold in your hand, very high repetition rates, and very low costs. Again, because this is a solid-state laser, we can externally trigger it, so we can move very, very fast. So this can be integrated into very fast scan systems. And finally, we have a very sensitive interferometer. So here's the system. That was the source laser. This is our entire receiving interferometer. This is the total delivery system, the head. So again, non-contact, mostly for inspection of composite parts. And then a real-time operating system in there so that we are imaging in real time as we are scanning through the system. So again, we presented this last year. One of the great characteristics of this system, again, unlike previous laser ultrasound systems, is that it's as good as the best contact systems in terms of sensitivity, and with the speed and compactness is pretty much equivalent to the best of contact ultrasound systems. So what can you do with it? So that's what we will talk about in the next 7 or 8 minutes here, is how can it be used for material evaluation applications. So the first one we've looked at is porosity in composite materials used in the aerospace industry. So material porosity obviously strongly influences the strengths and is a critical parameter which is used to characterize and qualify materials. Typically for ultrasound speed and attenuation measurements can be used to access the porosity, but they're literally integrated over the entire sample thickness and can be quite variable because they need reflections from surfaces of these irregular parts. What we looked at is can high-resolution imaging actually of the porosity be used to quantify, or can be used to quantify porosity in these same types of samples. So these are typical scans. If you're not used to them, let me just show you. We are very high-resolution ultrasound, so we're actually seeing the individual ply layers within the composite structure. In the back wall, this lower frequency signal is the back wall reflection we see. And what you're looking at is the high-frequency images that are obtained as in six different samples as the porosity increases. You can see at these very high porosities, you can see disturbed wave fields as is characteristic of the reflections and scattering that you would get from the pores. The question is, can you quantify this? So to look at quantification, we first take those images and we low-pass filter it to remove the structure signal. So the signals corresponding to this periodic structure within the composites are removed, and we can just look at this back wall reflection. So for ultrasound attenuation and speed measurements, we can make them, just like in conventional contact systems, using this information. However, we can also directly image the porosity, as is shown here. And using a measurement which is similar to that used in medical ultrasound called the integrated backscatter, we can relate the magnitude of those scattering to an estimate of the pore densities. So how well can we do? Well, here is what's done traditionally. That is the estimation with ultrasound speed, which is in red, and that's compared to a weight measurement, which is a gold standard for these samples. And what we can see is there's a good correspondence between the independent measurements of porosity and the ultrasound estimated. However, there are very large errors, especially in the high porosity samples, when you're trying to make the measurements based on wave speed. However, when you do measurements based directly on the imaging and the reflected signals, we see much smaller errors and a closer correspondence to the actual porosities in there, except for the largest sample, or largest porosity, where we can have some shadowing. Here, this is a sample that would never be used in the field. These are the areas in which we're going. So you get a very, very high correspondence and very, very, very low errors. So this is a way to measure porosity in the field, non-contact, at very high speeds using this system. Okay, next, what about another application? Heat damage. Very important issue in real samples used in aerospace, and this is a set of samples we got from some of our Boeing colleagues, which took test samples and heated them for 15-minute exposures at temperatures ranging from 200 degrees Fahrenheit to 650 degrees Fahrenheit. I'm sorry, in the aerospace industry, they still use English units. We're looking at things clearly. When you get up to 650, you can see the delaminations with your eye, some discoloring with your eye, but it's very hard to see what is potential internal damage at the intermediate temperatures that are there. So again, we look at it, so we make images of these samples. Here's the high-frequency representations. Again, when you're up at these high temperatures, we can see this disruption. If we filtered, we would see delaminations and others that are there. However, at these lower temperatures, we really don't see anything different. But do we? Well, here's a case where we take the opposite approach, is we now look at the actual high-frequency structure signal itself, and that is shown as a spectrum over on this side. So this is the signal amplitude we would get as a function of frequency. And we compare that structure signal, which is the peak in the spectrum, for what we have at 200 degrees versus the 600 degrees, we see that there is a redshifting or a displacement of the frequencies to lower frequencies. Having observed that, we can come up with a very simple signal processing procedure based on autocorrelation modeling or autoaggressive modeling to estimate this center frequency, that peak frequency, at every position within this image to look at the effective structure signal that is in there. When we do that, we get images like this. If you compare the mean frequency, say at the low frequency, to the high frequency, you can see that we have a much higher mean frequency as we expected. However, we start to see a fairly monotonic degradation in the signal as the temperature increases. If we average over a very small area, just a few millimeters on the side, we have a very robust measurement of this mean frequency as a function of the temperature. Meaning that we can clearly see the full delaminations and partial delaminations with just conventional B scanning, but we can also image and quantify the change in the physical structure of the composite at these mean temperatures well before they go into a failure mode with delaminations. And so this becomes, again, a high-speed, non-contact, in-the-field way to monitor heat damage on composites used in the aerospace industry. Okay, finally for composites is I'll show you the last example, which is looking for impact damage. So what this is an alternate display method. So remember that we make B scans through the cross sections. However, because we rapidly scan, we can take that three-dimensional data set and rotate it and just display C scans going in through the depth of the composite. That's what we're doing here. So it's low-pass filter, so we remove the structure signal, and we're just looking at damage that results through the depths of the composite when it is impacted at this site by just a ball dropping, a standard mode. And what you'll see here as you're rotating through layers, you see a rotation of the damage that occurs as a result of the change in orientation of the plies, of the fibers within the plies. And so you can follow that structure. So that's where the damage is, and you can follow it as you go with depth as it rotates from layer to layer in there. And so you can quantify the damage in those layers. When we showed this to our aerospace colleagues, they first thought these were X-ray images that we're showing, but no, these are these non-contact high-speed ultrasound pictures of this. Okay, let me conclude just to say that what I've shown you is mainly in composites and just longitudinal waves. The same system can be used for a lot of different applications. We can do all mode types. We can do, as I said, in the composites, mostly compressional waves, but we can do surface waves, shear waves, Lamb waves, all the different structures, just changing the shape of our excitation beam in optics. And I'll show you an example of this in metals. So here's a simple case we've shown in metals. We can produce a source which is like a surface wave source, so it's a finger source, and then our detector is displaced about 5 or 6 millimeters away from that. We can then record the propagating surface wave along the surface and can do surface inspections of metals very, very quickly, very easily, again, non-contact. And here we just have a simple crack, surface crack in a metal, which when we image is a piece of cake that you can see very, very simply. No problem at all. We can also look at things like welds. So again, using the a few millimeters propagation, we can see that the signals that we see when we're outside the weld versus within the weld. We can measure, quantitate wave speed within the weld. Again, very rapid scan, single shot, high speed, non-contact measurement, and from that be able to determine the quality of that weld from the surface wave measurements. So let me conclude I just did a quick potpourri of different applications for this. We've looked at a lot of things from wrinkles to heat damage to impact damage, the laminations in the composites and metals. We've looked at things like shear wave images, surface waves, which I've shown you, and also now looking at surface waves to quantitate residual stress. So let's remind you what the system can do. It is multi-mode operation, again, fully non-contact laser based system, but can be used in longitudinal surface, shear waves, Lamb waves, and anything you can construct based on the excitation regime. The total cost of this system, my goal was to be under $50,000. We're actually at about $55,000, but it'll be under $50,000 probably in about a year or two with a couple of the lasers get cheaper. We can scan at greater than 1 kilohertz, so as like you do in contact scanning. There is no reference arm. You can take this interferometer and throw it on the floor, and it will still work. Okay? There's no balancing. There's no 3 PhDs in the feedback loop to make this work. It fits in a backpack, so you can carry it anywhere around to do that. It has high sensitivity. It's equivalent, for those of you who are transducer people, it's equivalent two-way insertion loss is about 8 dB, so it's about as good as you're going to get with the best contact transducers. The alignment is no problem, reduced to surface, and it has an adjustable bandwidth. We've been able to work at this from 100 kilohertz up to 100 megahertz with exactly the same system. So I want to acknowledge Boeing, who have been our partners in this and have funded this, and a research center within the state of Washington who's done that. Thank you very much.